So assuming a 5% level of significance, we're
Are you testing them individually or jointly?
individually.
Okay.
So are we assuming that that everything we're working with is two-tailed? So assuming that the critical value for 5% is 1.96,
Yes, it's
are we
two-tailed.
also
So
assuming on
it
the other side it's negative 1.96? So if it's within that range, then we reject the null.
yes, if it's
Okay.
outside, if it's outside of that range, you reject the null.
Okay, yes, if it's outside of that range, we reject the null. Exactly.
Yes,
Okay,
absolutely.
cool. Thank you.
So for now, Lily and everybody else, it's a two-tailed test unless we tell you specifically otherwise.
Got it.
Okay.
Awesome. Thank you.
Okay. So last time I was talking about, let me record. Did we ever finalize the date of the exam? I think we did. Last time I said that already we had talked about April 6th, which is the day after we come back from spring break. But I offered you last class to do it Thursday of that week, yes?
Thursday would be great.
So that I can use, so Baruch reopens April 5, which I believe is a Monday. We meet on the 6th, Tuesday. I use the entire class on Tuesday to review for the exam. By then, you would have studied, and then we can answer questions and are pointing in the right direction, and then do the exam on Thursday. Okay, who asked me that question? Yes, Nikhil, okay. All right. So last class, okay. So what have we done? I took, and because again, remember, this is a financial econometrics class. It's an econometrics class. So I have to do econometrics things. I will not kill you with them. I will not overdo with them, but I have to do econometric work. So let me begin to record, okay?
This meeting is being recorded.
Okay, so one way of doing that is we are going to be talking about autoregressive model, AR model, moving average model, ARMA model, Gauch models, but we really don't have time to prove everything. And plus, some of those proofs, even for AR1, you see how deep they are. You see how dense they are. And it can be really involved. If you doubt it, repeat everything I have done for AR1, repeat for AR2, which I gave 2 years ago. I gave the class as extra credit on the exam, and it takes a long time, but they did it at home, brought it into the exam, and I asked them questions. So, but what I'm hoping to do is work almost completely with the simplest model, AR1. Show you how to do the proof, like I've been doing. The textbook is not great. Many of these textbooks are not great because they want to conserve space. So that's why I'm writing by hand. I write step by step by step by step. Now, you know what's funny? All those steps I wrote for AR1, you can use them for AR50. Okay, God help you in proving mean and variance and autocorrelation for AR50. It will take you forever, but if you have forever and you follow the steps I gave you for AR1, bingo, you can get it done with a lot of time. So what I've been trying to do is prove completely with AR1 and then let it go. So that after spring break, when I begin to talk about moving average, I would say, this is the mean, this is the variance, this is the autocovariance, this is the autocorrelation. I won't prove it to you anymore. I'll just say, remember how we proved it for AR1? If you apply the same steps, you get these equations. But I will need for us to use the equations, do R, calculate them using R, interpret the results, and move on. Okay, so that's why I have done it. So let me finish what I started last Tuesday, and then I'm going to spend not more than 5 minutes finishing it up. Okay, so I promise. All right. So let me get. So I think I got to page 5. So I showed the autocorrelation at lag 2. I did the same process. I showed the autocorrelation at lag 3. I did the same process for lag 3, okay? All right, and then, so let me get the other ones. God, I ran out of my voice in making those presentations. Sorry. Okay, so this is the next page. So this is the autocorrelation for lag 3. And I said we can do it for lag 4, for lag 5, for lag 6, so on. But you got the pattern last class, that the pattern is that the autocovariance at any lag S or any lag L is equal to the coefficient of the, the phi1. Remember, the AR1 is XT plus phi1 XT minus 1 plus white noise, mean 0, okay, constant 0. So that coefficient phi1, if it's lag 10, if I want to find autocovariance at lag 10, then it will be the coefficient of the XT minus 1, the phi1 to the power 10, the variance of the white noise divided by 1 minus that coefficient squared. Okay, this coefficient, the phi1 is always squared in below here, but on top here, it is raised to the power of the lag. Okay, so I showed you that. And then I said, now let us convert autocovariance to autocorrelation. Now, remember from your Finance 37 class, 3710 class, or your statistics class, what is correlation? Correlation between correlation between A and B is equal to covariance between A and B divided by the standard deviation of A times the standard deviation of B. But in this case, we don't have A and B. B is A, is auto. So we are looking for correlation between A and itself at another lag. So here, if I want to find the autocorrelation at lag 0, I divide the autocovariance at lag 0 by the autocovariance at lag 0, which is variance at lag 0, which is variance divided by variance. So the autocorrelation at lag 0 is 1. We know that. Everybody knows that. Lily, you know that because you keep telling me, is it 1? I always remember you with that. Autocorrelation at lag 0 is 1. This is why. The autocorrelation at lag 1 will be the autocovariance at lag 1 divided by the variance. Variance is autocovariance at lag 0. The autocorrelation at lag 2, and we use this little t, this tau. The autocorrelation at lag 2 is the autocovariance at lag 2 divided by the variance. The variance is autocovariance at lag 0, and so on and so forth. The autocorrelation at any lag 3, any lag S, any lag L is equal to the autocovariance at lag L divided by the autocovariance at lag 0. Okay, so you know this. I'm just repeating it. And then finally, let me do the final one. Where's the final one, please? Okay, so finally, I come in here. So what is the autocorrelation at lag 1? I'm sorry, please, everybody, I discovered a mistake a couple of hours ago. This should be this should be 0. The first one should be 0. This one should be 1, and this should be 2, 3, and so on. So it should be 0, 1, and 2. Sorry about that, okay? I didn't catch it on time. So please make a note. This should be 0, this is 0, this is 1, and then everything else is correct, 2, 3, and so on. Okay. So the autocorrelation at lag 0, everybody, look, the autocorrelation at lag 0 is autocovariance at lag 0, which is the variance, divided by autocorrelation at lag 0, which is the variance. That's 1, which is phi1 to power 0. Autocorrelation at lag, please change it. This should be 1. Autocorrelation at lag 1, this one is correct. This is autocovariance at lag 1 divided by autocovariance at lag 0, which is 0. Remember on Tuesday, I said the difference between the two autocorrelations is this phi. So this thing, this part here cancels this part. So it is phi to power 1. So the autocorrelation at lag 0 is phi 1 to 0. Autocorrelation at lag 1 is phi 1 to 1. Autocorrelation at lag 2 is phi 1 to 2. Autocorrelation at lag 3 is phi 1 to 3. Danny, my man, where is Danny? Huh? Oh my God, it's the end of life. Danny is not here. Alec, are you here?
Danny's here.
Ah, is Danny here? Okay. Danny, what is phi? Can anybody tell me what is phi again?
Phi is the constant in front of the equation.
Phi is the coefficient of the lag x variable. Is that right?
Yeah.
Yeah, that's what you mean. Okay. So in other words,
So can you do that again?
Okay.
Can you do that again?
Okay. Everybody, please indulge me. Okay. I'm going to send you a chat now. Okay. So equations. Let me just make up an Ar1 model. Zero mean Ar1 model. X of t equal 0.8 times 0.8 times x of t minus 1 plus u of t. All right. Please bear with me. I just sent, oh my God. I sent it to somebody privately. It's okay. I'm sending it to everybody now. Everybody to Le Monde. Paste. Okay. Everybody, please look at your chat, okay? This is an Ar1 model. Why is that so? Why is this an Ar1 model? Anyone?
It has one lag.
It has x to 1 lag on the right-hand side.
Yeah.
Period. This is a zero mean Ar1 model. Why do I say zero mean?
Because there's no mean in front of that coefficient.
There's no constant.
Yeah.
Okay, exactly. Because for it now to be a zero mean model, then I'll have something like this. I'll have something like this. A plus. Okay. If it's like this, I just sent you guys a chart now. You see that? This is not a zero mean Ar1 model. What is the mean of this model? It will be A divided by whatever. We proved that. But because this A is not 0, this is not a zero mean Ar1 model. Okay. Can anyone tell me for either the zero mean or the one with A, which one, what is phi 1 in both of them exactly? Thank you, my man, Danny. Phi 1 is 0.8, okay? Good. I hope nobody has a question about this. If you have a question, just ask me, okay? Why phi 1, that is the notation we use. Okay. So everybody, for either of those, especially for the first one with the zero mean Ar1, can anybody tell me what is the autocorrelation at lag 0 for that model? What is it?
1.
It's 1, because 1 is equal to phi 1 to the power of 0. So autocorrelation at lag 0 is 1. What is the autocorrelation at lag 1? At lag 1, the autocorrelation is what?
0.
At lag 1.
Phi 1.
It's phi 1. Look, can you see my cursor here? Can you see me circling this thing?
Would that be 0.8 in the example?
It will be 0.8 to the power of 1.
To the power of 1.
That's the autocorrelation at lag 1. What, can anybody take a wild guess? For that model, zero mean model I sent you by chat, what is the autocorrelation at lag 2? Don't give me the answer. Tell me how you arrive at the answer.
0.8 raised to the 2.
Point,
Raised to 2?
0.8 raised to the 2. That is 0.64. Is that correct?
Yes.
What is the autocorrelation at lag 11? Don't give me the answer, but tell me how you determine the answer.
Phi raised to the 11th power.
What is phi in my example?
0.8.
Again, so 0.8 to the power 11, that is the autocorrelation at lag 11. So you and I, Lily, I'm talking to you because you and I are always discussing this in class. So if I want to calculate not the autocorrelations now, but if I want to determine the autocorrelation function, what do I do? For each of those lags, 1, 2, 3, up to maybe 10 of interest, I calculate 0.8 to the power 0, that's 1, 0.8 to the power 1, 0.8 to the power 2, 0. So, and then I draw the graph of those autocorrelations I just calculated on the y-axis and lags on the x-axis, and I join those points. That is the ACF. Is that correct?
Yes.
Good. So now we know what to do. We know what is the equation for the mean, the expected value of the mean of a zero mean Ar1 model. We determined it before. It's 0. If it is not a zero mean, but it has that constant A, then it will be A divided by 1 minus phi. We determined that. Look at your proof, my handwritten work. When it's on Blackboard, the mean of an Ar1 model. What is the variance of an Ar1 model? Everybody, what is the variance? The variance of an Ar1 model is sigma squared is the variance of the white noise. Homoscedastic white noise is constant at every lag. So it's sigma squared, where sigma is the standard deviation of the white noise. Okay, so take the standard deviation, square that, divided by 1 minus phi 1. So in my example, if the standard deviation is 0.5, then the variance of the Ar1 model will be 0.5 squared, that's the variance, 0.5 squared, that's the variance of the white noise, divided by 1 minus phi 1, 0.8 in my example. So we proved that. Then what is the autocorrelation at every lag up to lag 10 for this Ar1 model? Okay, up to lag 10. At lag 0, 0.8 to the power 0, that's 1. At lag 1, 0.8 to the power 1, that's 0.8. At lag 2, 0.8 to the power 2, that's 0.64. At lag 3, 0.8 to the power 3. At lag 10, at lag 10, 0.8 to the power 10. If you plot all those numbers on the x-axis and correspondingly the lags on the, if you plot all those autocorrelations on the y-axis and then correspondingly the lags on the x-axis, and you join those points, you will see that for AR models, the ACF is an exponentially declining curve. 0.8 to the power 0, 0.8 to the power 1, 0.8 to the power 2, 0.8 to the power 3. Any number less than 1, if you keep raising it to the higher power of more than 1, it's falling, and it's falling uniformly. I will show you tonight in R, okay? Everybody okay? All right.
Professor,
Yes, who is this?
I don't mean to jump ahead, but would that be a -1 for Kendall's tau because it's like
No.
down?
No. That's a different concept.
Okay.
Okay, yes. All right, so it will be exponentially declining. I will show you tonight if my computer behaves and my R behaves. I'll show you in a few minutes. Okay, so everybody, one of the things you and I are going to be doing in this class after spring break is I'm going to ask you, go get data from Yahoo. You already did. is it an Ar1 model? So your company, the numbers you have, is it an do they follow an Ar1 process? Do they follow an autoregressive process? Well, one way of looking at it is draw the Acf, draw the autocorrelation function. If it's declining exponentially, bingo, that's one way of knowing. But that's a necessary way, but that's not a sufficient way. So a necessary and a sufficient way, bam, is you look at the Acf. If it's exponentially declining smoothly, you have to look at something else. And that something else is called the PACF, partial autocorrelation function. So I'm going to show you tonight, okay? Partial autocorrelation function. Those of you who are math inclined, I am not going to hold anybody responsible for this in this class. But your book, I think it's page either page 6. I think it's page 60. Has a very nice discussion of it. But I don't need, if you read that page, I don't need for you to even read the equation. But those of you who are math inclined, partial autocorrelation function or partial autocorrelation is something similar. If you remember Echo 4000, when you moved away from simple linear regression to multiple linear regression, if you have simple linear regression, 1y and 1x, then the beta attached to the x, what does it mean? It means when that x goes up by 1, your y goes up by beta. So for example, again, I'm going to put it on chat, everybody. I'm going to remind you what you did in Echo 4000, okay? So let me just write on chat now, and an OLS, an ordinary least squares thing, okay? Plus 1.9, 1.9, 1.9 times x. Okay. From me to everyone, you see you have run a regression and you got your intercept to be 3.5 and your slope to be 1.9. So this is your regression equation. Okay, guys? Now, what does 1.9 mean? I'm sure you remember. 1.9 means that if x increases by 1, by how much does y increase? Anyone?
1.9.
1.9, thank you.
Is that like 1.9 the slope?
Yes. That's the slope, okay? All right, now look at this. Now, everybody look at this. Plus x plus 2.7 times x of 2. Just bear with me, okay, everybody? Just bear with me. I apologize. Minus 3.4 times x of 3. Okay. What is the difference between the former equation and this new equation? Anyone? The first one was a simple linear regression. This second one is what? Multiple linear regression. Is that correct? Yes, I need to hear from somebody. Yes?
Yeah.
Okay, now, what is the interpretation of that 1.9 in this multiple linear regression model? Is it the same? Is it exactly the same as the interpretation of 1.9 in the former one? No. In the first one, please, you guys, look at the first one. In the first one, the simple linear one with only one x, let's call that only x. Let's call that only x1, okay? So the equation I gave you before, I didn't put the x1, I just put x, but let's assume it's x1. In that equation, it means that if x1 goes up by 1 unit, y goes up by 1.9 unit, period. Only one x there. But in the multiple linear regression, if x1 goes up by 1 unit, y will go up by 1.9 units. Given that, what happens? Given that x2 and x3 will stay the same. So in terms of calculus, 1.9 is partial derivative of y with respect to x1. Do you remember partial derivative? That's little squiggly d. Remember that crooked d, remember? Come on, you guys remember?
Yeah.
Just yes. So 1.9 in the multiple linear equation is the partial derivative of y with respect to x1. But in the simple linear regression where there's only one x1, only nothing else on the right-hand side, 1.9 is the derivative of y with respect to x1. How do we write that d? Straight up. Remember, the d is straight up. But for the multiple linear regression, the d is crooked. We call it del in calculus. It's a crooked d. So the same way ACF and PACF. PACF is the partial. ACF is the straight up derivative. I'm going to leave it at that. That's the most complicated way I'm going to describe this. I want to move on. Please read it on page 60. I will explain it again and again and again because we're going to be using PACF several times. But what I want to show everybody now is how we can, bam, nail it. Say that is an autoregressive model. So if I give you a set of numbers and I ask you, is this set of numbers IBM, Microsoft, or Apple? Either one. Does it follow an AR1 process? You will look at the ACF. If the ACF is declining like this, that's a hint. That's a necessary condition. A sufficient condition would be, you look at the PACF, and the PACF must have a particular structure. And in fact, by looking at the PACF, you will say that this is an AR1 model, this is an AR model, but it's an in addition, it's an AR1 model, or an AR4 model, or an AR10 model. Because it's sometimes, if I give you IBM and I ask you, is that an AR model? You say yes. I'll ask you, is it AR1, or is it AR2, or is it AR5? So if you look at the ACF, and then you look at the PACF, with a little bit more experience, you will nail that thing. Okay, so that's what we're going to look at now. Sophia, extra credit, yes. Okay, all right, so that's what we are going to look at. Any questions at all? Okay, so this is what I'm going to try to do. Fingers crossed. I am going to, because I do research, I find that that's what professors do. I have tons of R programs. I copy them. I put them in. I save them. So if I need to do something, I say, how can I do it the quickest way? So this is what I'm going to do. I am going to show you now. I'm going to simulate an AR model. It's like what you were doing in your previous classes. It's like you go to Excel and you use a random number generator to generate a normal distribution. Okay? If I want to do Jacques Berra, and I want to show you how to use Jacques Berra for a normal distribution, I can go to Excel, tell the random number generator, can you generate for me a normal distribution with mean this, standard deviation this, and Excel will give me a set of numbers that come from a normal distribution, and then we can test Jacques Berra and see whether Jacques Berra will tell us it's a normal distribution. So what I'm going to do now, I'm going to, in R, hopefully no problems, I'm going to simulate an Ar1 model. So I'll tell R, give me a set of numbers that follow an Ar1 process. And then when R gives it to me, to us, then we're going to look at the Acf, and then we're going to look at the PACF, and then we're going to see, because we know already that is, those numbers follow an Ar1 process. Then we're going to see what the Acf looks like, and we're going to see what the PACF looks like. And if I simulate Ar1, then the Acf and the PACF must tell us that that is an AR model and an Ar1 model. Okay, that's what I'm going to do now. If it doesn't work, trust me, I will give you the program, and then you try it. It will definitely work for you because it worked for me earlier on, okay? But because I went to give that presentation to the dean and the council, I didn't, usually when I want it to work in class, I shut down my system, clear everything I did before, and then do it again afresh with you in class. I didn't do that because 1 second I finished there and I came to you. So please bear with me. If it doesn't work, I'll send you all the codes, okay, properly defined and annotated, okay? Are you with me, everybody?
Yes, sir.
Okay, all right. So this is what I'm going to do now. I have my, where is it? Okay, here it is. Okay, you guys see it? All right. Don't worry if you don't understand these commands. I'll give you these commands, and then when you play with it at home, it will make sense to you, okay? So the first thing I want to do is I want to simulate an Ar1 model, okay? Please tell me, Lily, do you see this?
Yes, I can see that.
Okay, so again, I know I drive some of you crazy when I run it line by line, but please bear with me. I'm going to run it line by line, okay? All right, so I want to run the first line. So I do run. Okay, so it ran. So what am I doing? I have told R that I'm getting ready to ask R to simulate for me an Ar1, an AR model, okay? So I put it in form of ARIMA 100. Remember, an Ar1 model is really an ARIMA 100. Danny, my man, I want the AR coefficient. So this 0.5 is phi. You understand?
Yeah.
Okay, and this SD is 0.1, standard deviation of the white noise process. So can somebody tell me what is the variance of the white noise process I'm using here? What is the variance? Tell me, 0.1.
0.1 squared.
0.1 squared, thank you. Okay, so my phi one, so I want R to generate for me an Ar1 process. Give me 200 numbers, see, 200 numbers, okay? 200 numbers of an Ar1 process. So I'm going to generate a list with 200 numbers, line by line 200, randomly taken from an Ar1 process, all right? And so the command is arima.simulation. Okay, so let me run that. Run. Okay, so it ran. Okay, now, because I want to show you some other things, I also want to simulate an AR.8 model because I want to change, I'm using a phi1 of 0.8, and I also want to use a phi1 of minus 0.8. Why is that so? Because if you have an AR, for example, Ar1 model, the shape of the Acf is different depending on whether phi1, the coefficient is positive, or whether the coefficient is negative. So I want to show you both right now, okay? All right, so I am going to at the same time, so this is AR1.8 because, because I want the phi1 to be 0.8. The standard deviation of the white noise, I'm going to keep it constant all through, okay? So this is AR1.8. So let me run that and have it ready. So look, the bottom left, it tells me, it didn't give me an error. So far, so good, fingers crossed. Now, let me run. So far, R has generated for you and I 200 numbers from an AR1 process with coefficient phi1 0.5. And the other list of numbers is 200 numbers, Ar1 model process with phi1 0.8. Now, let me do the last one. I want to generate an Ar1 model minus, m minus 0.8. So here, the phi1 is minus 0.8. I hope you can see this, minus 0.8. All right. So let me do that. And I run it. Okay, fine. Now it's ready to generate it for me. So the first line prepares it, and the second line, it generates it. Okay, so no error so far. Can I go on while we're at it now and just generate Ar2 and Ar3 so I can show you? Okay, so let's do that. I'll generate Ar2. I'll do it together. Remember, for Ar2, let me remove this. For Ar2, it's ARIMA 200 because the I is 0, the MA is 0. And because it's an AR2, I have on the right-hand side xt minus 1 plus, so I have phi1 xt minus 1 and phi2 xt minus 2. So that's why I have two phis. So phi1 here is 0.5, phi2 is 0.3. Again, white noise standard deviation is 0.5, is 0.1. Okay, so let me do these two together now. Sorry, but before I send it to you, I will annotate it. I will describe it on the side, okay? So that if you repeat it at home, you follow what I'm saying. So here I didn't describe anything on the side. So I'll do it before I give it to you. Okay, so now we have generated an AR2 model with, again, 200 numbers, 200 observations. Let's just go ahead and do AR3. Okay, I do AR3. Okay, so now we've done that. So let's begin to do the Acf. Okay, so there are some things I won't run. Okay, so let me run this because I want to show the graph. I want to show both of them on the same graph, on the same side by side. All right, so let's run Acf. So this is Acf of the AR1. So I'm saying Acf of the AR1 set of numbers that we already generated. So I run it. It doesn't show me. Okay. Do you guys see that at the bottom right?
Yes.
Okay. For this first one, what is my autocorrelation at lag 0? Anybody?
1.
1. What is my autocorrelation at lag 1?
0.4. 0.5.
It's 0.5 because phi1 is 0.5. What is my autocorrelation at lag 2? 0.5 squared. What is my autocorrelation at lag 3? 0.5 to the power of 3. So you see, because I have 200 observations, I have many of them, and this is kind of compressed because I want to put the PACF right next to it, okay? All right, but later I will run it wide so you can see it. But for now, so this is the first time some of you are seeing the PACF, or maybe not. Let's see. So I run it. So that is the PACF. Okay. The PACF, everybody please, this PACF does not begin at lag 0. It usually begins at lag 1, okay? So everybody, again, I'll blow it up very soon. So at lag 1, everybody look here. How many of those bars are not significant? How many of them are beyond the bounds?
Only one.
Only one, only the first one at the lag 1. So the PACF, okay, so the ACF, if you join these numbers, is exponentially declining. It's a smooth curve declining. The PACF is not declining, it's just straight up bars with only one outside of the range. That tells you that it's an AR model, but an Ar1 model because only one of those bars is beyond the boundary, okay? Do you understand?
Say that last part again.
Okay. If it's an Ar1 model, if it's not Ar1, if it's an autoregressive model, AR, of any P, Ar1, Ar2, Ar3, it doesn't matter what the number is, what the lag is. If it's an AR model, it's exponentially declining. The ACF. Look at this ACF. At 0 is 1, then 0.5, then 0.25, and then it's declining. It's smooth declining. You are going to see it when I put the ACF by itself. The PACF does not decline. It's just like bar graphs, straight up lines, straight up line, straight up line. There's no sequence. There's no smooth decline. There's nothing. There's no structure. But the PACF will confirm if it's an AR1, if it's an AR model, the PACF will have no pattern. But if one of the bars is outside of the boundary, then it's an Ar1 model. If 3 of the bars are outside if 3 of those straight up lines are outside the boundary, then it is an Ar3 model. Yes, Danny?
Isn't there 2 out because the lag 0 isn't that out? Isn't that out of the boundaries? So isn't there 2 lines out?
No. There's no lag 0 here. Look, this is lag 1. Okay, lag 1, lag 2, lag 3, lag 4, lag 5.
I got
Okay?
that. Yeah.
Okay, so what's your question?
So lag 0 doesn't exist for partial ACF?
No, we're not looking at lag 0. ACF, we're looking at lag 0 is always 1 for ACF. But for PACF, what concerns us, lag 1, lag 2, lag 3, lag 4, lag 5, okay?
Okay, so
Okay.
ignore lag 0 completely for the
Yes.
Okay.
Yes. Okay. So let's move on. So let's look at the PACF. Let's look at the ACF and PACF for lag 0.8. Okay. So the ACF for 0.8 is like this. Okay, this one is a little bit screwy. Now, as you will notice, again, you will play around with this. And when I send you this, play around with different numbers of phi1. As phi1 goes towards 1.0, when phi1 is 1.0, that model is a random walk. So sometimes it's crazy. It behaves, as you approach 1.0, the curve behaves in a crazy way, but there is still that smooth decline, okay? All right. But because I'm dealing with 200 numbers, maybe many more lags beyond 20, so it's kind of compressing it, okay? All right, but so I'll show you. So this is, let's go on. Look at the PACF here. What kind of auto-regressive model is this? Is this an AR1 or AR2 or AR3? Anybody?
AR1.
It's an AR1 because only in lag 1 did it penetrate. Let's look at lag 2 quickly, okay? Let's look at lag 2, okay. Is anybody asking? No, nobody's asking me. Okay, let's look at lag 2. Let's see ACF for AR2. This is ACF for AR2. You see it's again declining smoothly. Let's look at the PACF for AR2. Okay, how many numbers break the bounds? Well, there's a third, that is 1 and 2. There's a third one here that breaks the bound, but it breaks it by a little bit. So if you want to be thoroughly precise, this is like an AR2 and nothing in the third lag, nothing in the fourth lag. Then at lag 10, there's a small breakthrough. Let me tell you all. Let me tell everybody. After the spring break, I am going to introduce another way to confirm what the lag is. Remember, when we tested for normality, we can eyeball a graph called the QQ graph. If you eyeball it, you can say whether those numbers are from a normal distribution or not. But to be certain, we do the statistical test called Jacques-Berra. For time series here, we're looking at AR or MA or AR-MA or ARIMA. We can eyeball the graphs. The eyeball is what we're doing now. We're looking at the ACF and the PACF. After spring break, I'm going to show you a statistical test that we can use to nail it down. So the first place to begin is look at the ACF and PACF and get some idea. For this model, I'll get some idea that it's an AR2 model. But because at lag 10, there's a little bit breakthrough, I'll say, okay, let me perform the statistical test to confirm. Do you guys understand this? Do you understand? Somebody talk to me. If you don't understand, let me know, I'll say it again.
Yes.
Who said yes? Natalie. All right.
So you're showing us tools how to identify.
Number one, I'm showing you your tools, how to eyeball, okay? To eyeball to try to identify one, whether it's an autoregressive model and not an MA model, or not another type of model. It could be AR, it could be MA, it could be AR, MA, it could be ARIMA. We have not discussed MA, but for now, when we discuss MA, you will see that it's different characteristic than this one. But for an AR model, the way to identify that a series of numbers follows an AR process, number one, look at the ACF. If it's smoothly declining, okay, that's a hint. When you look at the PACF, it's not declining, it's straight up bars. That confirms it's an AR model. But AR what? Is it AR1, AR2, AR10?
That's when you check the bars, right? To see.
That's when you check the bars to see which one penetrates.
Right.
In this case, two of them penetrate very strongly. You see that, right?
Yes.
But one of them is kind of weakly, it's not making up its mind. In this case, I can tell you from experience, it's an AR2. You guys, you saw me generate an AR2 with R, right? You saw I generated AR2. But suppose we didn't know. Suppose you went to Yahoo and got the numbers and you get PACF like this. You say, okay, now I suspect it's an AR2. by eyeballing the ACF and the PACF. But to confirm, I'm going to do a formal statistical test. Are you with me?
Yes.
That test, you don't know what it is right now, but after spring break, I'll come to class and I'll do it in R for you, okay? And show you, just like we did a formal statistical test with Jacques Berra to see whether it's normal or not.
Okay.
Okay? Because again, let me talk about normal. Remember, I defined a normal distribution as a distribution with coefficient of skewness 0 and excess kurtosis 0. Now, but you can look at those two numbers. They are not 0. So you say, okay, they are small. I'm not quite sure. But how can we be very sure? Bingo, we do statistical test called Jacques Berra. Are you with me?
Yes, Professor.
Okay. So that's what we are going to do in this case. So the first place to begin is with eyeball with ACF and PACF and get reasonably 95% certainty is an AR. But because of this little annoying thing that, this one in lag 10, we say, okay. I'm sure it's an Ar2 model because I generated an Ar2 model. Okay, but suppose I didn't know. Now I'm going to do a formal statistical test that will nail it down for me. After spring break, I'll show it to you, okay?
That's the Jacques Berra, right?
It's not the Jacques Berra. It's a different name, okay?
Uh,
Jacques Berra tells us normality, but this test is different. I'll show you. Don't worry, after spring break, okay? Now, let's look at the Ar3 quickly. Sorry. So I'm looking at the Ar3. Ar3, that's the ACF for Ar3. Again, you see smooth decline. And then let me look at the PACF for the Ar3. Okay, what do you think here? Here, I see only 2 bars working, okay? I probably chose the wrong numbers, but again, this, because I know it's an Ar3, we're going to do formal statistical tests after the break, after the spring break to see. There should be 3 lines breaking through those 2 bounds. Okay, but now let me go and draw these graphs one by
Professor,
one.
you mean the 3 bars that do not pass the line, right?
No, there should be 3 bars that pass the line here.
Okay.
For it to be an Ar3. But I don't know why this is not working. Maybe because I bunched them together. But let us see. Let me draw each one separately, okay? All right. So let me tell R to give me each graph by itself. Okay. So I do that. That's successful. Okay. Now let me plot the original time series that I generated, the Ar1 I generated. Bingo. So this is the Ar1 model that R generated for us. So this is the plot, okay? Now let me plot the ACF by itself. So I won't bunch it up. Okay, this is the ACF, okay? This is the ACF for 0.5. So this is the, at 0 lag is 1.0, at lag 1 is 0.5, at lag 2 is 0.25, and so on and so forth. So this is smoothly declining. Now let me draw the PACF. This is the PACF. You see that? Only one is breaking through. You see that? Okay. In the interest of time, let me just kind of move quickly forward. Okay, please, everybody, bear with me a few more minutes. Okay, sorry, I started class. Sorry, I started class late today. So let's go to an Ar2. Okay, let's forget all this 0.8 and you know what? Let me do 0.8 because I want to show you what the graph looks like by itself. Okay, so this is no. Let's do only 0.8. So let me plot the series. That's the series. Okay, please everybody bear with me. This is the ACF of the series of 0.8, again, smoothly. And let me draw the PACF for 0.8. Remember, this is still an Ar1 model, but the phi is phi 1 is 0.8. Again, only one bar breaks through. Now everybody watch. Let me do the AR1, but the phi 1 is 0.8. This is the graph of the numbers themselves. Now let me draw the ACF for minus 0.8. Phi 1 is minus 0.8. Aha. You see? Because it's going, if you guys can see me on camera, it's going from up, it's going smoothly down, and then from below, it's going smoothly up. Because at lag 1, everybody walk with me here. At lag 1, what is negative 0.8 to the power of 0? What is it?
1.
1.11. So you see it. At lag 0 is 1. At lag 1, what is negative 0.8 to the power of 1?
Negative 0.8.
You see that? So whenever it's lag 1, lag 0, lag 2, lag 4, lag 6, it's positively is declining like this. And whenever the lag is 1, 3, 5, and so on, it's going from up down. So this is how. So suppose you go to Yahoo and you download some random stock, Apple or not Uber, whatever, and you plot the ACF and it's looking like this, that means your phi 1 is negative. You understand that, everybody? Okay. Let's look at the PACF. So again, I'm going to give you this program, this command, and you play with them, okay? And then I'll give you some more after the spring break. This is the PACF. How many lines are breaking through? How many lines?
Only 1.
It's 1, but the line is faced downwards, negative. So that tells you this is an Ar1 model with negative coefficient. You understand?
Yes.
Okay. Quickly, let me do Ar2. Ar2. If you have to leave, please leave because I'm recording this, okay? All right. So this is the plot for an Ar2. Let us look at let's look at the ACF. This is the ACF, you see? The ACF is declining smoothly. So this tells me it's an autoregressive. It looks like an autoregressive model. But let us look at the ACF, the PACF, because, okay, let's look at the PACF. What do you see? How many bars are breaking through?
2.
Only
2.
1. 2. Yeah.
2. This one at like 0, at like 1, and this one, and then this crazy little one. This one is really pissing me off. And this one is very close. So if I have these kinds of results and I'm not sure, here I am sure because I generated an Ar2 model. Maybe my choice of coefficients is screwed up, okay? But suppose I went to Yahoo and got these 200 numbers and I'm looking at things like this. This one strongly at 1, this one strongly at 2, but at 10 is just weak. Then I'll perform the formal statistical test. I'll show you after the break, okay? Then let's look at AR, let's look at the 3. I'll plot the time series. Okay, this one shows a little bit of trend. So I didn't do quite a good job in selecting the coefficients. Again, it is tricky to select the coefficient because you have to select the coefficients so that their sum will be less than 1, the magnitude, the absolute value for stationarity. There are many conditions. So I must have selected this wrongly, but I think it will do for this exercise. This is the ACF. You see it is smoothly declining. Many of them are beyond the 2 lines. This is the ACF. Let us look at the PACF for 3. Okay, it should be 3 beyond the line, but no. Okay, so here, again, I will do a formal statistical test. Here, I see 1 and I see 2. Actually, when I ran this before class, early morning before I began to prepare for my presentation, when I ran this at lag 3, this one broke through. Okay, this one broke through. So I don't know what's happening, but I'll give you the comments and you guys work on it. But I will check my choice of phi 1, phi 2, phi 3. Now, everybody, please, just, I promise you, this last thing. At the beginning of the semester, I put on Blackboard a file that contained GDP and blah and so on. You remember I put it on Blackboard for you. Now, I didn't generate that number. Those are real numbers. Now, anybody tell me, this is not generated numbers. These are real numbers. Tell me what kind of process this is, okay? Tell me if this is an AR1 or not, okay? So I have to set it up. I have to bring the data in, okay? So again, I ran this before and I give this to you. It's on Blackboard, if you remember. This is my macro data. So let me run this, this one. Okay, it's there. So I'm going to install a couple of packages. This might be where I may run into trouble because when I've installed it before and I didn't shut down my computer, it will give me an error message. Okay, it's giving me all kinds of warnings. Okay, so I'm installing it. Let me library it. Let me bring it in here. It's still working. Sorry, guys, okay. All right, so let me library it. So I'll bring it into my R. Okay, and then let me, because I'm not sure which package now, this is an old version of R. Let me also bring XTS, just in case.
You're running them as comments, Professor.
Yeah, thank you. Danny, is that you or is that you, Alec?
It was Alec.
Thank you. You guys are so smart. Thank you so much. I really thank you.
You're welcome.
Yeah. Okay. Thank you so much because I'm in a hurry here. Okay, so I'm installing them. And I'm going to library this. I'll library this. Come on. Okay, I'm not sure which one I need now because I don't have the command in my head. So I'm going to library this. Okay, so I'm ready. All right, so now let me go do the ACF. So let me make it a time series data and blah, 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 so I won't run into trouble. I promise this is the very last thing I'm going to do. So I put it in data one, and I don't need to see data one. Let me pick up GDP, all of GDP, only GDP because there are many columns. I pick up GDP, and let me just verify that it picked up GDP only. Okay, so it gave me only GDP. Now let me go do the ACF. So now everybody, this is a quiz for everybody. I'm going to do the ACF of GDP. What do you think this series looks like? Well, it looks like an AR1. It looks like an AR because it's smoothly declining. Now, after the spring break, I'll show you how to determine phi 1 because we're essentially going to do a regression, kind of like an OLS regression. It's not really OLS, but we're going to do a regression so as to, for this GDP, determine what the phi 1 is. I'll show you that, okay? And now let's look at the PACF, to see whether it's AR1 or 2. What do you think this process is?
AR1.
Strongly AR1, bingo. All right. Sorry, guys, I kept you way beyond time. I kept you for 15 minutes extra. So this is what I'm going to do, okay? I am going to, maybe over the weekend, I will annotate this very well. I'll put the pound sign and describe what each line does. There are too many commands here that you will not use. I'll make it compact. I'll copy it to Word, and I'll upload it for you. So over the spring break, as you study for the exam, you can play with it. Now the exam, what am I going to? Trust me, for this exam, I will test mostly concepts. Okay, I'm not going to have you, this is not a class about R. I'm not going to ask you during the exam, please run R for me. No, I'm not going to do that. Instead, I can run R and show you the result and ask you the meaning of that result, okay? But what am I looking for? I will test concepts. What do I mean by concept? If the ACF, what does the ACF mean? Okay, if I give you a graph of the ACF and the PACF, what do you suspect it is? Is it an AR1 or AR2 or none? Okay, I haven't shown you MA, I haven't shown you ARMA, I haven't shown you ARIMA. So if I ask you, the question would be, is it an AR or not? That's all we have done up to today, okay? And then I may ask you for definition of stationarity, but I will not define, I will not say define stationarity, no. I may give you a statement or two, and I say, do you agree that these statements mean that the series is stationary? So that's the kind of thing I'll be doing for this midterm exam, okay? So please study for concepts. I will not ask you to do an R program during the exam. I will not say, look at this data, use quant mod. No, that's crazy. I won't do that because that's not what this class is about. But I will focus on concepts.
What
Okay?
will the format of the test be?
I'm thinking now maybe multiple choice,
Amen.
because this class is only 1 hour. How many minutes? 1 hour, 15 minutes. I mean, what can you do in 1 hour, 15 minutes? So I'm thinking it will be like multiple choice, okay?
Great, thank you.
Okay, all right. So don't forget, Tuesday the 6th, we are not going to be doing the midterm exam. We discussed that last Tuesday. What I'll do is over the weekend, when I'm done with everything this week, I will put it on Blackboard, okay? Say, remember, the exam is not on the 6th. When is the exam again? On the 8th, on Thursday. And that will allow me to review. So the entire class of the 6th, I will not teach anything new. So if you feel you're confident, then don't come to class, just study. But on that day I'll come, you please do not come on the 6th and expect me to teach you all over a particular topic. I will not do that because we don't have time. I will take questions from you. I will remind you of some things. So on the 6th is a review. I'm not teaching. If you have not studied over the spring break, you will really not get anything from the review. Okay, I promise you that. You may get something, but you will get more if you actually studied very well over this spring break and then come to the class on Tuesday the 6th with questions. I beg you, don't get frustrated, and I will not be frustrated, okay? Let's come in. You all have studied, and then we'll go back and forth with questions and answers, okay? I think it will be very, very more productive. And if one of you is taking up too much of my time, hey, my friend Danny, you know how much I love you to death. Lily, you know, by the way, where's Roxolana? I haven't heard from her today. Is she here? OMG, Roxolana is not here.
Well, it might not be accurate because we're past class, so she may have had to leave.
Oh, okay.
Let's cut her a break.
I'll cut her a break. Okay, I was just kidding, by the way. So, but if Lily, I know you won't, but if Lily, you're asking me 1 million questions, after 2 or 3, I'll say, Lily, please, can I just go to another person? I'll come back to you. You understand, right? So I'll kind of share it among the class, okay? So everyone have a nice break, okay? Be safe, everybody.
Professor?
Yeah, who is this?
Alec.
Alec, my man. Yeah, talk.
How are you doing?
Yeah. Hold on. Let me stop recording and then we can.
The recording has stopped.
Okay. Yes, Alec.
So I was trying to do the homework.
Okay.
Maybe I'm bothering you with homework questions. It's just I need some guidance because when I do the box peers, and when I do the t-test, so The t-test that we're doing, is it
For
just
individuals.
for individual lags, lag 1,
Yes.
lag 6, lag 9, and lag
Yes,
12,
yes.
right?
So the t-test, you are trying to see whether the ACF at lag 11 or whatever is 0 or not. Only
0 or
that
not.
one.
Okay. And then when you want us to do a joint, when I run the box peers, I get the joint. The box peers does it for values up to 30. So up to 30 lags. Is that okay?
I did it up to 12. Maybe I'm misunderstanding.
Wait, did I restrict you in the homework?
No, box peers, you said that use the box peers and Leung box statistic to test for joint statistical significance of each of the simple return series. So here you want us just to run the box peers just like that?
Honestly, at this point, I really don't care. Whatever lag you use, just tell me what lag you use.
So you want us to use a lag for box peers?
Box peers, R will select a lag for you, or you can specify the lag.
Okay.
When you are typing in box peers, R will give you a parenthesis and tell you many things. One of them would be, one of the choices could be lag equals, Lily, if you want only 12, then specify lag of 12. It will stop at lag 12. But
So
if you don't specify anything, then it's okay. Then the R will use the default value for your version. And whatever the statistic is, then look at the p-value for your conclusion, okay?
Okay, so you want us to take, to do a joint box peers for both?
Box peers and Leung box, they are joint tests.
Okay, okay, I need to review that. Page 49, is that right? Is that where we should look like?
Yes, page 49, but yes, I gave you the page for homework. But also remember, I did an example in class,
Yes,
remember?
you did.
Yeah, so go to that example first.
I did exactly what the example, okay.
Okay, so then after doing the exam, because in the example, I use only 5 lags, yes?
Yes, you do a lag 5, yes.
Okay, but if you go to R and you don't know how to specify the lags, or you don't want to, it's okay. Just use the command in the book.
So you do a box test and the lag 5. That's what you did in class.
Yes, I did. I did box peers and Leung box. I did both of them in class.
Yeah, but when you did the box peers, you didn't specify anything. So you did box peers and then the data set that we had, it was Y.
Yes, because in class there were 5 lags.
Okay.
Okay. But for R, if you want to specify the lags like Lily did, you can say lag equal to 12. Or if you don't want to, just forget it. R would select a default lag for you and then make your conclusion based on that, whatever R selected for you. But just let me know in your write-up that you didn't specify any particular lag.
Okay.
Is that okay?
Awesome.
All right. Okay.
Thank you.
All right. You guys have fun.
Professor, just one quick question.
Who is this?
Lynn?
Yeah, you submitted already, right?
Yeah, I submitted already.
Okay, but you know, because it's not due yet, if you still want to change it, you can go ahead and change it.
Oh, okay, I see.
And the same for, I think, Roxolana, many of you already submitted, but because it's not yet deadline, you can still update it if you think or you want to. William, you have a question, I'll come to you in a second. Yes, Lynn, go ahead.
No, I'm just wondering, would there be like any practice material for the midterm or
No, because this midterm exam is different from the one I normally do in class. Because in class at Baruch College, usually I have more time, I can give you more time, so the format is different. But here, because it's on Zoom, I'll give you only multiple choice. At Baruch College, I don't give you multiple choice.
Oh, okay, I see.
So I don't have any multiple choice to give you.
Oh, okay.
Because this is on Zoom. I mean, this pandemic is driving me crazy, but that's the true story. For this class, I never gave multiple choice. But I will do that to this year because we're doing it on Zoom. And we really don't have to. At Baruch College, we can begin at 5:50, and I can let you guys go until 7:30 or 8 if there's no class coming into that classroom. You understand? But we cannot do that on Zoom because many of you have to go to other classes. I have other things doing immediately after this class. Okay, Lynn?
Yes. Thank you.
Okay.
Yep.
But on Tuesday, the 6th, come with questions and which I'll answer more questions. Okay? All right. William, you had your hand up.
Hey, yes, Professor. Thank you. I just had a quick question in general. It's a general one about about AR model.
Yes.
And I just wanted to ask this question to put this class into better perspective for myself. So typically an AR model is under the assumption of a non-linear information. Is that correct?
Linear.
Oh, it's linear.
Yes. Everything we do in this class up to chapter 2 is linear. When we after chapter 2, we get into chapter 4, variance. We are working with variance. Variance is squared. So the variance equation is nonlinear. So everything we shall do in chapter 4, there are nonlinear models. William, thank you for that point. Remind me again. Even if you don't remind me, I will state it. Everything we do in chapter 2 is a linear model. Look at your textbook in chapter 2, beginning page, I think page 40, page 50 or 49, where it begins, the heading is white noise, okay? So from there on, it discusses for you white noise, and it tells you linear time series model.
Okay.